Good morning to one and all. Welcome to our favorite video channel Sri Ganitha Vijnana Sarvaswam. This is your maths teacher B. Ramesh Kumar, JL in Mathematics. We discuss system of linear equations, direct methods. Now we discuss the method is Gauss-Jordan method to solve the given system using Gauss-Jordan method. Now our method name is Gauss-Jordan method. We see Gauss-Jordan method. First of all, we discuss the working procedure of this method. Let us consider one system. Let it be, let a1x plus b1y plus c1z equals to d1, a2x plus b2y plus c2z equals to d2, a3x plus b3y plus c3z equals to d3. Now here we take three equations with three variables. First we write this system in matrix form. So the matrix form is A1, B1, C1, A2, B2, C2, A3, B3, C3. Now we take the coefficients of the variables. So now the first equation, coefficient of variables x, y, z are A1, B1, C1. Now it can be written in first row. Similarly, we take the coefficients of x, y, z, A2, B2, C2 already written in second row. Similarly, same procedure follows for third equation also, A3, B3, C3. This is coefficient matrix. Now here the variables are x, y, z. We write in column wise. That equals to the constants also we write column wise in RHS side. This is also column matrix. Now here this matrix is called coefficient matrix. This matrix is called variable matrix. This matrix is called constant matrix. Here let it be the coefficient matrix will be taken as capital A, variable matrix will be taken as capital X, and constant matrix will be taken as capital D. Now here the matrix form of the given system is Ax equals to D. So this is the matrix form. Now here we write the augmented matrix of given system. Here the augmented matrix. Now we follow the augmented matrix. So augmented matrix equals to, first we write the quotient matrix, that is A. Now besides quotient matrix we write constant matrix, that is D. So this matrix is called augmented matrix. So here the augmented matrix is quotient matrix we write first of all A1, B1, C1, A2, B2, C2, A3, B3, C3. Next we write the constant matrix column wise, D1, D2, D3. So this is augmented matrix. First we observe that in the augmented matrix, first row, first element is either 1 or 0 or non-zero. Now we can apply, here we can apply elementary row transformations. Only use elementary row transformations, not only column transformations. Only row transformations but not column transformations. For example, we take column transformations, here not using row transformations. Now generally we take row transformations in this method. So first of all, the first element of first row is either 1 or non-zero or 0. Now compulsory the first element of first row is must be 1. We can apply row transformations, it can be reduced to 1. That is the first step. So the element which is the position of 1 1 will convert it to 1 applying row transformation. Any type. So this is the first step. Now using this one, then we convert it to first elements of second row and third row are zeros. Using 1, which is 1st position. The first elements of second and third rows will convert to zeros. It convert to zeros applying row transformations. At the same time, here we observe the second row, second element, which is 2 2 position, is either 1 or 0. For example, this will be non-zero. We apply row transformations also and convert it to this will be 1. Directly, already using row transformations, it will be converted to 1. Now using this one, applying row transformations, and the remaining second elements of first row and third row will be converted to zeros. That is the next step. So here first we observe second row, second element is either 1 or not. We observe two-tooth position element is either 1 or not. If this is not equal to 1, first it will convert to 1 by applying row transformations. Next, using this one, second elements of first row and third row will convert to zeros. So this is the next step. Similarly, we follow same procedure. The third element of third row is either 1 or not. We can apply these transformations. First we will convert it to 1, and using this one, the next third elements of first row and second row are zeros using this third element. This procedure follows in third row also. So this is the working procedure of this one. Next, the augmented matrix will be converted to, here A1 will be converted to 1, B1, C1 are zeros, A2 will be converted to 0, and A3 also 0, B2 will be converted to 1, C2 is 0, this is 0, and third row, third element also 1. Now here this will be converted to, coefficient matrix will be converted to unit matrix, and similarly D1, D2, D3 also will be converted to some values D1 dash, D2 dash, D3 dash. So here this is unit matrix, and these are the converted elements of the column matrix, constant matrix. So here we observe one is the coefficient of x. Now x equals to d1 dash. So x equals to d1 dash. Similarly, here one is second row, second position, one is coefficient of y. So that is y equals to d2 dash. Similarly, z equals to d3 dash. So this is the solution of the given system. This is the working procedure of Gauss-Jordan method. Here same procedure follow, second row second element, third row third element also. Now using these two elements, the remaining elements of first row, second row, third row are zeros. Now here we observe the principal diagonal elements must be converted to ones and the remaining elements must be converted to zeros, applying that elements, principal diagonal elements, and we get reduce the remaining elements are zeros. So first of all, this will be converted to unit matrix, coefficient matrix, and remaining constant matrix d1, d2, d3 will be converted to d1 dash, d2 dash, d3 dash. Here we comparing 1 is the coefficient of x, and here 1 is coefficient of y, here 1 is coefficient of z. Now it will be simplified, x equals to d1 dash, y equals to d2 dash, and z equals to d3 dash. So this is the solution for the given system using Gauss-Jordan method. Now we can solve the problems. Now we solve the problem. The first problem is solve the system x minus y plus 3z equals to 5, 4x plus 2y minus z equals 0, minus x plus 3y plus z equals to 5 using Gauss-Jordan method. Now the given system is here. So first of all, it will be converted to matrix form. So the matrix form of the system is, here we take coefficients of x, y, z. So 1, minus 1, 3, 4, 2, minus 1, minus 1, 3, 1. This is coefficient matrix, and the variable matrix is column wise, column matrix x, y, z. And similarly, we take the constants. This is also column wise 5, 0, 5. So let it be, this is A, this is X, this is equals to D. Now the matrix form is AX equals to D. So this is the matrix form of the given system. Next we take augmented matrix. The first step is, here we take augmented matrix. Though first one is augmented matrix, that equals to, here first we write coefficient matrix, and besides the coefficient matrix we write constant matrix, that is D. So AD. So this equals to, here the coefficient matrix is 1, minus 1, 3. Similarly 4, 2, minus 1. And third row is minus 1, 3, 1. And the constant matrix is 5, 0, 5. So this is constant matrix. So totally we observe this matrix is called augmented matrix. Now the augmented matrix is here 1 minus 1 3 5, 4 2 minus 1 0, minus 1 3 1 5. Here the first element of first row is 1. So first we observe this element is 1 or not. Already here this first element is always equals to 1. Now using this one, the remaining first elements of second row and third row are zeros. We can apply row transformations. So here multiply with 4 and subtract from second row, this will be 0, and adding third row and first row, this will be also 0. So here we take row transformations are R2 changes R2 minus 4R1. Similarly R3 changes R3 plus R1. Now the reduced matrix is, here the first row will not change. Here first row is 1, minus 1, 3, 5. Second row, so here R2 minus 4R1. So this is 0. Here 2 minus 4 into minus 1. So plus 4. 2 plus 4 is 6. Similarly, minus 1 minus 4 into 3. So minus 12. Minus 12 minus 1 minus 13. Here this is 0. Minus 4 into 5 minus 20. So this is second row. Similarly, the third row. Adding first and third row. So first element is 0. Here 3 minus 1. This is 2. Here 1 plus 3. This is 4. Here 5 plus 5. This is 10. So the resultant matrix is 1 minus 1 3 5, 0 6 minus 13 minus 20, 0 2 4 10. So here the second row second element is 1 or not, we observe. So this is not equals to 1. Now we observe third row, divide with 2, the second element is 1. Now we take the transformation, R3 changes R3 by 2. So the resultant matrix is first row does not change, second row also does not change. In third row 0, 2 by 2, 1, 4 by 2, 2, 10 by 2, 5. So here we interchange second row and third row. R2 interchanged by R3, that equals to 1 minus 1 3 5. First row does not change. Second row third row interchanges 0 1 2 5, 0 6 minus 13 minus 20. So here we observe the second row second element is 1. Now using this one, the second element of third row and first row will be converted to zeros using row transformations. Here R1 changes R1 plus R2. Here minus 1 plus 1 0. Similarly R3 changes R3 minus 6R2. Now using these, so 1 plus 0 1, this is 0, this is 5, this is 10. Now second row does not change. Third row 0, this is 0, minus 13 minus 12, minus 6 into 2 minus 12. So minus 25, minus 20, minus 30, minus 50. Now here we observe, in this one, third row will be divided to 25, minus 25. This is also reduced to 1. Now using the transformation, R3 changes R3 by minus 25. Therefore, the reduced matrix is 1 0 5 10, 0 1 2 5. First two rows does not change. In second row, third row is changed by 0 0, minus 25 by minus 25. This is 1, minus 50 by minus 25. This is 2. Now using this one and reduce third elements of first row and second row are zeros. Now the transformation is R1 changes R1 minus 5R3. Here multiply with 5 and subtract from first row, this will be 0. Similarly, R2 changes R2 minus 2R3. Here multiply with 2 and subtract from second row, this will be also 0. The reduced matrix is here using first transformation R1 minus 5R3, this is 1. So this is 0, 0 minus 0. So this is 0, 5 minus 5. This is 10 minus 2 into 5, 10 minus 10, this is also 0. In second row, the second row operation is R2 minus 2R3, 0 minus 0, 0. Here 1 minus 0, 1. So 2 minus 2, 0. Here 5 minus 2 to the 4, 5 minus 4, this is 1. So the third row is same, 0 0 1 2. Now we observe, in this augmented matrix, the first quotient matrix will be converted to unit matrix. Similarly, the constant elements, here 505. In the original augmented matrix, the constant matrix is 505. It will be reduced to 0 1 2. Now here the solution is x equals to 0, y equals to 1 and z equals to 2. So this is the solution for this problem. Now we check solution to verify the equations. Now here we take x equals 0 minus 1. So minus 1 plus 3 into z value 2. 3 into 2, 6. 6 minus 1 equals to 5. So first equation satisfied. Similarly second equation x equals 0. So this is 0. 2 into 1, 2 minus 2. 2 minus 2 also 0. Similarly third equation minus x minus 0. That means this is 0. 3 into 1, 3 plus z value 2. 3 plus 2 equals 5. Now this solution will be satisfied the total given system. Therefore this is the solution of the given problem. So here we observe that compulsory the given system will be converted to unit matrix. We apply row transformations. So here also more problems in more cases. So this will be not converted to unit matrix. So applying row transformations, it will be remaining elements also zeros, and here we observe the rank of the quotient matrix is 2 or 1 also. So here unique solution, compulsory there exists unique solution if the quotient matrix equal rank of the quotient matrix equals to rank of the augmented matrix. Here the rank of the quotient matrix is 3. Similarly the rank of the augmented matrix equals to 3. So therefore rank equals to 3, which equals to number of unknowns. So here there exists a unique solution. Some more problems, we apply row transformations, it will be converted to some zeros and ones. Now here we observe the third row are all zeros. Some more cases. Similarly, they may remain in second row also zeros. Here the rank of the quotient matrix equals to either 2 or 1, and rank of augmented matrix is also 2 or 1. Now here there exist infinitely many solutions also. So here there exist infinitely many solutions. Now we take some x or y or z. Anyone, we take some scalar and simplify the remaining variables in terms of case. So this type of solutions also exist for this in this method also. So compulsory here the quotient of matrix equals to 3. So here either the rank of the quotient matrix is 2 or 1. Then there exists a infinite number of solutions also. And for example, for any time also, here the rank of the quotient matrix is not equal to rank of augmented matrix. In this case, there exists no solution also. So this type of solution also exists for this method also. So this is the working procedure for more problems also. So more cases so exist in this equation. So similarly, this procedure can be followed for more problems to understand this method. So thank you.